Hello, this video is entitled Numerical Integration. Let's take a look at this definite integral right here. From 1 to 3, the square root of 1 plus x cubed dx. Now if we wanted to evaluate that definite integral under traditional methods, we couldn't really do it because this function does not have a natural antiderivative or any kind of antiderivative. You can't algebraically work it out and then plug the numbers in. So we have these numerical techniques, and we're going to illustrate how to use a couple of those in this section, and talk about the TI calculator a little bit too, and it has its own method. Now let's look at this called the trapezoid rule. There's two rules we're looking at, trapezoid and Simpson. So trapezoid, F's got to be continuous on your A to B. The trapezoidal rule, so we're saying it's approximately equal to B minus A over 2 times N, where N is the number of subintervals. Let me kind of change this. All right, there we go. Subintervals and the how much you're going to break it down into, how many pieces. Now, on both these rules, the larger number of subintervals, the better the approximation. But for students' cases, I'm not interested in having you, do something long and tedious, and that sort of takes the fun out of it at that point. Yes, for example, we're going to use pretty much 4 subintervals for test or quiz type questions, just to keep it short and sweet and not wear you out too bad. But yeah, we'd have a lot more terms in this formula if it was 16 subintervals, for example. But so you're going to start out, you're figuring out the function value, which is whatever you're integrating right here, your f of x. You're going to evaluate that at A. The last one has to be B. So to follow this pattern, you've got to have it spaced out properly. So the delta x, the change in between each x value, is calculated as B minus A divided by N. So let's see here. But that's not, don't confuse that with this. This is part of the formula. B minus A divided by 2N times the sum of all these functions. You see the pattern? 1, and then it has 2 times each of these other ones. 1, 2, 2, 2, 1. So if there were more subintervals, it would be 1 and a bunch of 2's and then 1 at the end. So the breakdown for this one then is, since B is 3, up here, and A is 1, 3 minus 1 divided by 4, if we were using 4 subintervals, that would be 0.5, 1/2, that's 0.5. So that tells you how far apart you need to space these. So you would start at 1, x0 would be 1, then you would have 1.5, 2, 2.5, and that guarantees you'll finish exactly at what the B value is, which is 3. Now here's another example. Suppose you were going from 1 to 4, and you had 4 subintervals. 4 minus 1 divided by 4 equals 0.75. And then you'd start at 1, you'd go 1, you'd add 0.75, be 1.75, 2.5, 3.25, and you finish right at 4. All right. Now we're going to look at an example of this. I'm just going to go ahead and define both rules first, and then we'll apply both of them. So, yeah, you're going to see this worked out, don't worry. Now let's talk about the Simpsons rule, which is generally better. It's certainly better for lower number of subintervals. I've never tried. Maybe one day I'll try to do a trapezoid and Simpson rule for like 16 subintervals and see what I get as an answer. But the Simpsons rule is going to be a little bit closer for smaller subintervals to what the actual integral would be. Well, you can't really assuming you can't work it out, but if it was one you could work out and you compared it, this one would be closer. Alrighty, so the Simpsons rule. So now this is one difference is N has to be an even integer. For the trapezoid rule, that's not true. You could have 11 subintervals if you want to. This has to be even, and we're going to stick with 4 anyway, so that's not going to be a problem, but it does have to be even. Now the difference is this one is b minus a divided by 3n. And then look at the pattern of the coefficients here. It has to be even so it makes sure it stays on this exact pattern of alternating the 4s and the 2s. So it has 1, then it goes to 4, then it goes to 2, and then 4, and then 1. So the second one is a 4, and the next to the last one needs to be a 4. So for example, if it was 8 subintervals, it'd go 1, 4, 2, 4, 2, 4, 2, 4, and then 1. That's kind of confusing without seeing it, but don't worry about it. You would just alternate the 4s and the 2s, but you would finish to where the next to the last one would have a 4 in front of it. Now your delta x, the difference in the x values, is measured the same way it would be for the trapezoid rule. Same idea. You take b minus a divided by n. All right. So here we go. We're going to take that problem we just did, and we're going to use a trapezoidal and Simpsons rule with n equals 4, and we're going to round these to 4 decimal places. All right. So here's where I did that. I explained this one earlier, but 3 minus 1 divided by 4 is 0.5, so I'm just listing these out. These are going to be your x values right here. We've already talked about that. So to do the trapezoid rule, here's what we do. So the formula is b minus a over 2n, 3 minus 1 over 2 times 4, and we have to evaluate this, f of 1, 2f of 1.5, 2f of 2, 2f of 2.5, and f of 3, and we'll add all those together. And you can do these individually, write them down, and add the numbers, but let me show you how to do these in a TI calculator where you can do the whole problem in one step. Now, if you're just using a regular scientific calculator, that's okay. You can still do these individually and write them down. Just use even more than 4 decimal places. I would use 6 because you can always round at the end. You want to make this as accurate as possible, and I'll explain why here shortly. So you don't want to, make sure you use more decimal places at first and then round at the end. But if you have the TI, you can kind of do this all in one step. Now I kind of got it sort of nested down here. Now let me show you. You may see if you've never used the VARS, YVARS function before. This could be a new experience for you. Now I'm going to come up here, bring up my calculator. All right. So I was playing around with those numbers earlier. So let's see if that's still in my, okay. Now I'm gonna put this in as my function, y equal 1, like that. So 1 plus x cubed, like that. So there's my VARS. Now one way you could do this is, you can use a table of values, but the thing about the table of values, you'd still have to add up all those numbers. There's probably a command that will sum them all up, but in other words, I think what I'm about to show you is going to be a little bit easier, but so you're used to, you can put function values in tables and get the values right there, but you still have to add these up. So, no, I don't want to do it that way. Let's get out of that. Let's take a look at the problem again. Now the 1 over 4 comes from this right here. That'll be 2 over 8, so that's going to be 1 over 4 times all of that. So I'm going to have to make sure I've got that nested in parentheses for the whole thing here. So I'll have to be real careful. So watch what I do here. I'm going to go 1 divided by 4. There's my parentheses. Now maybe you've used this command before, maybe you haven't, but this is how you can do a single function value without having to do a table. If you go VARS, right there, YVARS, function, and our function's in Y1, so obviously if you had it somewhere else, but I can't imagine any reason why you wouldn't put it in Y1, but maybe you had something there you didn't want to get rid of, but you pick whatever it is. So in this case, ours is Y1, then you put parentheses. Oh, I didn't mean to put 2 of them, sorry about that. And our first one's going to be 1. I close the parentheses, so Y1 of 1 is the same thing as f of 1. It's this. So these are the function values. Now, I don't need that number individually because it's just part of the sum, the grand sum here. So I'm just going to keep going. Then it's going to be plus 2. I may not have to put the times here. It'd probably be okay if I did or didn't. It doesn't matter. I'll go ahead and do it. It's probably okay if you don't. It should know it's multiplication. VARS, y VARS, function, y1, and the next x value, according to delta x, will be 1.5. Close that off. 2 times VARS, y VARS, function, 2. Oh, okay, no, I thought I didn't put the 2 in front of it, but I did. Never mind. Thought I made a mistake, but I didn't. 2 times VARS, y VARS. Okay. It's probably get annoying. Listen to me say that every time. Now you see the idea. You can probably just watch. So here goes 2.5. And the last one will not have the 2 in front of it. So it'll just be the function value at 3. Close that off. Now I need one more right parentheses there to close off everything being multiplied by 1/4. So that's why I need that second set of parentheses. I hit enter. And then we wanted to round that to 4 decimal places. Sometimes I've been known to even use 6, 4, 6, whatever. And then you can see the answer right there in the screen. All right. And here I wrote down what the y1 was right there. Okay, let's see. Let's take a look at the Simpsons rule for the same problem. All right. Probably have the formula down here. Now here's some good news. You don't have to retype this entire thing. The Simpsons rule this is only because we have 4 subintervals. We had more than 4 subintervals. What I'm about to say would not be true. There'd be more changes than just 3. But with 4 subintervals, we only have to make 3 changes. So I can use the second enter feature in the calculator, which you'll see me do here in a second, and then go back and just type over those 4 changes. The only difference is this is now a 3n instead of a 2n on the bottom. And the second coefficient is a 4 instead of a 2. And the next to the last coefficient is a 4 instead of the 2. So I can change this. It's 3 changes without retyping the whole thing. So now we have 3 minus 1 over 3 times 4, which will be 2 over 12, which will be 1 over 6. So watch what happens here. I'm going to go second, enter. I'm going to scroll back to the beginning. Almost there. So I'm going to put a 6 where the 4 is, because it's now 1 over 6. I'm going to put a 4 right here. The next one remains a 2. And then this one becomes a 4. And that's it. All I have to do is hit enter now. And there it is. 62303. All right. And there it is. That's terrific. And there it is in the box. Right there. There's what the TI-84 gives you. Or TI whatever. I did it in Maple also. So I don't know what algorithm Maple is using, but it's a little bit different there. Probably even way more sophisticated than whatever. I think the calculator uses something called a Gauss-Croden algorithm, which is really not fit for human consumption. In other words, as far as trying to do that manually like we're doing with the Simpsons and the trapezoid rule, this is more for, easier for people to actually work this one out. That other one is kind of a mess, and it would not be, it's made for computers. This, you can do this we can do this as regular people here. So now, of course, this is an older version of the FNet. Now, the FNet now, obviously, the newer software, it shows the actual integral, the upper and limits of integration. So I'll put that in there real quick just to show you. Then I have something important to say about that. And that's going to be there we go. So there's what it looks like using the modern operating system. Now here's the important announcement I want to make on this is, for exam purposes, whether this is a multiple choice question or whether it's a worked out question, the TI calculator answer is not the correct answer. You cannot, so if it's a multiple choice question and you put it in the calculator and you see that answer there, don't pick it. It's not the right answer. Now the idea is the answers from the rules will be close to it. You can use it, you can use the calculator as a check to see if your answer's close, but do not pick the calculator answer, because I'm designing this to where I want the answers on the test to be the answers that you get by performing the rule. If that wasn't the case, then what's the point of me even doing the rule? So it's okay, but if you're using a scientific calculator that doesn't do the definite integrals, that's okay, because you don't really need it. You don't have to do it. But do not use that as your answer, because that will not be correct. But it will be close. It's only for checking purposes. So I want to state that real clearly. So you would just think, oh, I'll just stick that in the calculator and I'll pick that answer if that's one of the choices. I make it one of the choices on purpose in multiple choice, but it would be the wrong choice. All right, let's take a look at another example. I'll probably just get rid of this, whatever. Just call it example. It's probably, from an old book where it wouldn't be relevant anymore. Well, when I'm sitting here playing this, I'm not using I'm trying to do this on a non-touchscreen tablet here, so I'm going to try to just put EX there. Anyway, so while I'm messing around with this, we have the integral of the square root of x times sine of x. Definitely not solvable by hand. And from pi over 2 to pi. And once again, 4 subintervals. So like I said, in our world, we're going to stay consistent on the 4 subintervals. Just because I mentioned before, I just don't want this to be something that's too tedious and time consuming. Make that a little bit bigger format. So you see I have the delta x. Okay. So we take the pi divided by pi over 2. I might subtract pi over 2, excuse me. Pi minus pi over 2 divided by 4 is pi over 8. So that means the change in x needs to go from pi over 8. So it's going to go, since pi over 2 is basically 4 pi over 8, 4 pi over 8, 5 pi over 8, 6 pi over 8, 7 pi over 8, and then 8 pi over 8, which is just pi. So there's the proper spacing. So trapezoid goes 1, 2, 2, 2, 1, And then you have pi minus pi over 2, b minus a. For trapezoid, it's 2n right here, 2 times 4. So that's going to be, that'll be pi over 2 divided by a. It'll be pi over 16 will go on the front of that. So let's put it in the calculator and see what happens. All right, I'll clear that so we can start this over because we've got a new function and now we have pi in there. So I could type over the old ones, but I think this will be better. So now I want to clear that, put the square root of sine of x, square root of x times sine of x. All right, arrow out of this. Takes care of that. And so now we'll do, so it's pi over 16. And then we have the VARS, Y VARS, all that business. Now I'm doing this by moving a mouse around. I suspect that, you'll be doing this a lot faster. Using, I can certainly do it a lot faster on touching the keys, and I can do it this way. So 2. I'll do it without the times this time. I don't think I really needed the times, but it certainly wasn't. Well, we'll find out, won't we? This will be 5 pi over 8. Yeah, so I'm just moving the mouse pad along here, so it's kind of slow this way. And then 6 pi over 8, which of course is 3 pi over 4, but you don't have to reduce it. 2 plus one more 2. And let's see. Be 7 pi over 8 here. And then we'll finish that pi. The last one does not have a coefficient of 2 in front. Close the parentheses right there, and let's see what we get. And we can compare that to what I have before. Yep, that's it. So the trapezoidal rule to 4 decimal places will yield, go back up here, there's the formula, yields 1.4299. All right, so once again, 3 changes. So it's b minus a over 3n instead of 2n. So that puts 12 on bottom, so that makes the leading fraction now pi over 24, and then just change 2 of the coefficients to 4. And for exam purposes, I generally put, where you can do it, where you'll be able to do it this way. In other words, it'll be the same function, same limits of integration, same everything. 2 separate questions, one on trapezoid, one on Simpsons. So you'll be able to do this exact same thing. It doesn't matter which one you do first. You can do it the other. You could do Simpsons and then change it back to trapezoid. It'd still be 3 changes either way. There's a 4 there. 2. This becomes a 4 right here. So I guess we've proven that I did not have to put times in front of that. Okay, well, that's all right. Wasn't that much trouble to do it. So there it is right here. Correct Simpsons, 1.4583. I did it in the calculator. Like I said, you don't want to pick that calculator answer. But that's why you got to be careful not to round. That's what I was talking about. You want to, so that way, the way I'm doing it in the calculator, there's no rounding until the end, so it's going to be precise. Because the Simpsons rule will, sometimes be pretty close to the F and int rule. And this is, usually I don't like to have answers that close together, but in this case, I need to, because like I said, I don't want people picking the F and N answer as the right answer. So these need to be close. That's why even if you're doing it with any kind of scientific calculator, use a lot of decimal places before you add them up. Here you don't have to because it's already storing a lot of decimal places. So, all right, there we go. I believe we have one more here to close this up. Good news is, like I said, I don't think you have to, once you kind of do a couple of these, I think you'll have the hang of it. It's not something, this is not something like trig substitution or partial fractions or those complicated methods where there's not, there's just so many different varieties of ways you can ask the problem. Still try one or two of these. You got to make sure you get the answer yourself, but I don't think you have to spend a ton of time on this. All right. So let's see what we have here. This is from 0 to 4, the cube root of 4 plus x squared dx. So now we have b minus a over n, so it's 4 minus 0 over 4 equals 1. So then our values of x are just going to be 0, 1, 2, 3, 4. Just happen to be integers for this one. So the Simpsons rule is 4 minus 0 over 2 times 4. That's going to be 4 over 8, which is 1/2. And you can see the progression: f of 0, 2f of 1, 2f of 2, 2f of 3, and then f of 4. And, I said 5 decimal places this time. Okay. We just got to read whatever. I was wondering why I had 5 there, but I made it 5 for whatever reason. I don't know, but that's what I chose. Saying obviously it was consistent for the Simpsons. Made it 5, so all right, we'll knock this one out real quick and we'll be done. It's going to be the cube root Wait, let me clear this out and find that cube root function. Or I can just raise it to the 1/3, but yeah, I knew there was a cube root function there. 4 plus x squared. Oh, not times. All right, now I think I got it. So here we go. What was, I know the progression was, so it's 1/2 in front. Okay, so that's what I couldn't remember. 1 divided by 2, parentheses, f of 0, plus 2 f of 1 plus 2 and then 2f of 2, and now 2f of 3. All right. And then f of 4. So close that off, and then, of course, the 1 extra parentheses there to close off everything after that 1/2. There we go. Let me just, before I switch back, let's just do both, the other one right here, and we'll check. So, second enter. Got to go back. Well, I do have to go back, I'm sorry. Because now it's b minus a over 3n. So I'll scroll down. So it's 4 minus 0 over 3/4. So that's going to make that a 1/3 in front. So I want you to see that. So there's the 1/3. All right. And then change 2 of those coefficients from 2 to 4. We got it. So that's a 3. Four. 4. And that's it. So we should have 821222 for 5 decimal places for the trapezoid rule. Yes. And then let's check the Simpsons rule. 8.18235. Got it. All right. There we go. Oh, this last part is what I've sort of already mentioned verbally here during the video, was about, the calculator answer not being the correct answer that we want, because we want the goal is to get the answer using the rule. And I believe that concludes this video on the Simpsons rule.